Welcome to this explainer on the alkaline earth metals. Today, we're going to break down the properties, the atomic trends, and honestly, the spectacular chemical reactions of the group 2 elements. By the end of our time together, you'll be able to confidently lock down these concepts, from the microscopic electron shells all the way up to the macro-level fireworks they produce in the real world. Let's get right into it. Here's our quick roadmap for today. We'll start with the group 2 metals themselves, explore their reactivity trends, watch them react with water, oxygen, and acids, dive into those tricky stability rules, and then finish up with some incredibly cool flame tests. All right, section 1, the group 2 metals. Let's meet the alkaline earths. We're starting our journey right at the top of group 2, looking at the foundational elements you're definitely going to encounter on your exams. We've got beryllium, magnesium, calcium, strontium, and barium. Now, these silvery gray metals are noticeably harder and have higher melting points than their neighbors over in group 1. Why is that? Well, it's because they contribute 2 outer electrons to their metallic bonding, rather than just 1, which makes those bonds significantly stronger. And if you look at the right side of this table, notice how their atomic radius steadily increases as you move down the group. The atoms literally just get bulkier. Keep that in mind because that physical growth, it actually drives everything else we're about to see. Moving on to section 2, reactivity and atomic trends. This is the core rule of group 2. Now, what's really fascinating about this next concept is that it totally unlocks the reasoning behind almost every single chemical trend we're covering today. We need to talk about electron shielding. As we move down the group, each element gains a completely full, brand new electron shell. These inner shells act kind of like a physical barrier, literally a shield, which increases electron shielding and causes those 2 outermost electrons to be, well, much less strongly attracted to the positively charged nucleus sitting in the center. Because of that shielding, we get this strict chain reaction of events. And hey, here's a massive exam tip for you. When you're asked to explain a trend in reactivity for these metals, you absolutely must use these 3 specific steps, rather than just casually saying something like, oh, the atoms get bigger. So step 1, the atomic radius increases. Step 2, electron shielding increases. And step 3, because of that extra distance and shielding, the outer electrons are more easily lost. And the easier those electrons are lost, the more vigorously the metal reacts. It's really that simple. Okay, section 3, water, oxygen, and acids. Let's look at some laboratory reactions. Let's start with water. You know, a very common mistake here is confusing the way these different metals react with H2O. Just remember our trend, reactivity increases as we go down. So magnesium, sitting high up there, reacts incredibly slowly with cold water. I mean, so slowly it's barely noticeable. It sluggishly needs high-energy steam to actually produce magnesium oxide. But calcium sits lower down. It reacts steadily and pretty dramatically with liquid water, fizzing, bubbling, and turning the whole solution milky to produce alkaline calcium hydroxide. And by the time you get all the way down to barium, it reacts violently with liquid water, even generating enough heat to ignite the hydrogen gas it's giving off. So what happens when we burn them? Well, when burned in oxygen, these metals form solid white metal oxides. Magnesium is incredibly famous for this reaction. It burns with a brilliant white flame that releases so much intense light, it's actually bright enough to severely damage your eyes if you stare directly at it. Barium, down at the bottom, is so large and reactive that it actually breaks the standard rule just a little bit. It can take on extra oxygen to form barium peroxide when it's heated in an excess of oxygen. Now, if we toss these metals into dilute acids, things speed up considerably. All group 2 metals dissolve rapidly in dilute acids to produce a salt and hydrogen gas. The bubbling is immediate and it is vigorous. And if you're in the lab, you can easily verify that the escaping gas is indeed hydrogen. You just hold a lit splint over the test tube and wait for that famous, highly satisfying squeaky pop as the hydrogen ignites. Love that sound. Let's look at the basic character of the oxides these metals form. The oxides of group 2 metals are powerful bases that react highly exothermically with water to form hydroxides. If you take solid calcium oxide, which is often called quicklime, and drip water onto it, you can literally watch the solid crumble, expand, and visibly heat up as it transforms into slaked lime. Because they're so strongly basic, they are absolutely fantastic at neutralizing acids. All right, section 4, stability and solubility rules. This is an A-level deep dive. For our advanced viewers, let's look at the A-level rules governing how these compounds break apart when heated. This process is called thermal decomposition. So the crucial point here is how the size of the metal ion dictates its stability. Another critical exam tip for you, carbonates and nitrates become much harder to thermally decompose as you move down the group. But why? Well, it's all about polarization. The tiny magnesium ion at the top has a massive charge density. It acts like a powerful magnet. It strongly polarizes and distorts the bulky carbonate ion right next to it, which makes it super easy to break apart with just a little heat. But those larger ions, like barium, they have a lower charge density. They simply cannot polarize the carbonate anion nearly as effectively, meaning you're going to need extreme heat to break them down. This beautifully illustrates the opposing solubility trends you absolutely must memorize. Seriously, these two families of compounds go in completely opposite directions. Hydroxides become vastly more soluble as you go down the group, meaning magnesium hydroxide is almost completely insoluble, while barium hydroxide dissolves beautifully. But sulfates? They do the exact opposite. Sulfate solubility strictly decreases down the group. Magnesium sulfate dissolves easily, while barium sulfate is a stubborn, insoluble solid. And we actually exploit that stubborn sulfate insolubility in a classic everyday lab test. If you want to know if an unknown clear solution contains sulfate ions, you use barium chloride. First, you acidify it with a little dilute hydrochloric acid. This is a crucial step because it clears out any confusing carbonates or sulfites that might give you a false positive. Then you add the barium. If sulfate ions are present, boom, you instantly produce a thick, milky white precipitate of barium sulfate that simply refuses to dissolve. Moving on to our final segment, Section 5, Flame Tests and Applications. Let's get into some real-world chemistry. So, how do we quickly identify these invisible metal ions if they're already dissolved in a solution? Easy, we burn them. By dipping a clean nichrome wire into the salt and holding it in a roaring blue Bunsen flame, that intense heat actually promotes the outer electrons in the metal to a higher energy level. And when those electrons inevitably drop back down, they release that extra energy as incredibly striking, specific colors of visible light. Calcium gives us a vivid brick red. Strontium burns a deep, beautiful crimson. Barium produces a glowing apple green. Magnesium, interestingly enough, drops its energy outside our visual spectrum, so it gives no distinctive color at all. But you know, these properties aren't just fascinating lab tricks. They're absolutely vital to modern industry and medicine. That calcium carbonate, it's the foundational building block of the cement and glass in our cities. Calcium hydroxide is spread by the ton to neutralize acidic agricultural soil so our food can actually grow. Magnesium hydroxide, which we just learned is poorly soluble, is perfectly formulated as an antacid, like milk of magnesia, to safely soothe an upset stomach. That incredibly insoluble barium sulfate, you can swallow it safely as a barium meal to vividly illuminate your digestive tract for medical x-rays. And that beautiful crimson strontium flame we just talked about, that is exactly what gives red fireworks and emergency road flares their brilliant, life-saving color. We've covered a massive amount of ground today. Since you now intimately understand the micro to macro trends of atomic radius, the sheer power of electron shielding, and how all of that leads to extreme chemical reactivity, I want to leave you with this final provocative thought. Look at the very bottom of Group 2 on a periodic table. Knowing these strict, unbreakable top-to-bottom trends, how violently would the highly radioactive element radium behave if you somehow managed to drop a piece of it into a beaker of liquid water? What kind of unimaginable flame color would it produce? Keep questioning, keep exploring, and I'll catch you in our next explainer.